Hi, this is Professor Fernandez, and this is video 2 in lesson 23. So we're talking here specifically about trig limits, and we're going to do some tricky ones. You see 3 examples here on your screen from Calculus Simplified. I'm going to go through those in a minute. First thing I'll say is that you might want to check out the videos in lesson 5 and also in lesson 6. This one covers limits in general, two-sided limits, and also continuity. And then these videos talk about advanced techniques, for example, limit laws, rationalization, things like that. We are going to draw on all of the techniques and theorems and results that these videos touch on. So if you want a quick review of all that, head over there. Okay, so what are we staring at here? Let's take a look at this first example. Show that this particular limit equals 0. So we're going to do the same thing we normally do with every limit. We're going to try to see if the function we're looking at, in this case this, is continuous. If it is, then I can just substitute in this x value over here, and then whatever I simplify that output to is the limit. You can see that that's already a problem, because even from the arrow I've drawn, if I put in x equals 0 here, that's a problem. I'm dividing by 0. So this function that I've put in the box is not continuous at 0, so I can't do that. This is, again, one of the reasons why this problem begins to be tricky, and it will get a little trickier in a moment. So you might be wondering, I can't substitute in x equals 0. What do I do now? Certainly, you could try a table of values. So you could start substituting in different x values. You know, here's 0. It's undefined there. But different x values close to 0 to see what the function approaches. You could also try graphing. So that's first method, second method. You know, who knows what the graph of this looks like. The problem is that in both of these cases, you're only going to get an approximation to the answer, right? You're not going to be able to say for sure that the answer is something. You know, the way a computer creates a graph is that it literally plots a bunch of points. And it plots a lot, you know, so you can zoom in as much as you want, but still, a computer is finite. It does not plot all of the infinite number of points on this graph. Same thing with your table, right? Your table only plots a few values. So this is my way of convincing you that we want to try an analytic technique here, right? We want to do something with the function itself to help us find the limit. Okay, what we're going to do is a version of rationalization or unrationalization or just conjugate multiplication. Different people call it different things. What we're going to do is we're going to multiply the numerator and the denominator by the same factor in the numerator with a different sign. This is one of the reasons why some people lump this technique into rationalization or unrationalization, because that's kind of what we do sometimes when we have radicals involved in these limits. So again, I will point you to the videos in lesson 6, videos 6.1 through 6.3. But you can see there are no radicals here. Nonetheless, we're doing a similar thing. So we can think of this as a conjugate. Same factor as this one, except a different sign. Okay, so how do I proceed? Well, I'm now multiplying cosine times cosine, gives me cosine squared x. Notice this part will be positive cosine x, and this part over here will be negative cosine x. And then I have, oops, my marker disappeared. And then I have minus 1. Okay, and then in the denominator I have x times cosine x plus 1. You can see that this cosine x and that cosine x go away, and I'm left with cosine squared x minus 1 divided by this denominator. At this point, you might be thinking, you know, Professor Fernandez, you went from this to that. Looks like you've complicated the problem. How has that helped? And I would say, you know, it certainly seems that way, but let's just keep going. We see cosine squared minus 1. When you see a cosine squared, you might want to think sine squared. Why? Because sine squared and cosine squared are intimately related, right, by this relation. So if I start there and I subtract cosine squared from both sides, sine squared from both sides, I get that. So in other words, if I go one step further and I subtract 1 from both sides, I get this. And now I can use this to substitute in for the numerator, leaving me with minus sine squared x in the numerator. So again, that doesn't seem like it necessarily helps. You might be thinking, okay, I've just shifted things, but hey, at least this had 2 terms. This only has 1 term. So it has simplified a little bit. At this point, we are going to go back and pull in the limit because our job is basically done, even though it doesn't seem like it's done. How so? Well, let me go back and pull in all this stuff into the limit. So I'm just going to erase this up here, and then erase this over here, and then move this function up so we can see how this helps. Okay, so because this function and that function are the same, right, then we're going to say this equals the limit of x approaching 0 of this function. Again, you might be thinking, how does this help? I still have a 0 in the denominator. That is not good. But now let me do one thing. Let me suggest, first of all, let's pull out the minus sign, put that one out front. And then let me suggest that we split up the function we're looking at into this very special form. Again, you might be thinking, how would I ever know to do this? There are two answers. Number one, this is a tricky trig limits video. So number two, now that you've watched the video, you've learned another technique. So going forward, you might think to do something like this. Okay, so what have I done, right? I took sine squared x and I split it into sine x times sine x. Okay, and then I chose to keep the x with this first factor over here and to dump everything else into the second factor. Why would I choose to do that? Well, the reason is what I've written down here. So this is equation, just down here. This is equation 2.3 in the textbook Calculus Simplified. And this is a very special trig limit that we use often when we start doing tricky trig limits like the example we're doing now. It says that the limit as x goes to 0 of sine x over x equals 1. Which is kind of surprising because there's an x in the denominator, and you would think as x goes to 0, the denominator goes to 0, you're getting a problem. And indeed, if you're thinking of the value at x equals 0, it's not undefined, this function. However, the limit of this function is defined as x equals 0, and it's equal to 1. So this is what we're going to draw on. And by the way, there's lots of different ways you can prove that. There's some information in the book about that. So we're going to go ahead and draw on this result. And I'll scroll up so you can see that if I now write this as the product of two limits, so I'm using one of the limit laws, which says that the limit of the product is the product of the limits, provided that each limit exists. So we are going to look at each one of these limits separately. The first one, right, that's exactly this limit down here, so that's minus 1. And then let's look at the second one. Well, I'm now going to try the same thing I normally try. This is a new limit, so let's talk about continuity. This is a continuous function. This is a continuous function. The quotient is continuous so long as I'm away from where the denominator is 0. At x equals 0, if I just look at the denominator, cosine of 0 plus 1, cosine of 0 is 1, plus 1 equals 2. Hey, I am away from where the denominator is 0. So this function is continuous at x equals 0. So I can now just substitute in x equals 0. And that would be the limit. So the limit is this. And then now I continue calculating here. And you can see that things are going to work out very nicely because sine of 0 is 0. And then the denominator we just calculated is 2. So I get minus 1 times 0 over 2, which is 0. Once again, we get a 0. 0 is a popular answer for limits. Okay, so I'm going to say a little bit more about this example at the end of the video, but for now, it illustrates, again, what made this particular problem tricky, and also just pulling in some fundamental limits from trig functions. Okay, let's move on to this second example over here. This one's actually going to be a little faster. You can probably tell that by the amount of white space that I left here to solve it. And what does it say? It says, evaluate this particular limit, tangent x over x, as x goes to 0. Once again, we can't substitute in x equals 0 because the function is undefined there. And tangent of 0 is actually 0. So actually we get 0 over 0, quote unquote, right? If we try to substitute the 0 in for x. So we have to do something different. We could try playing the same game as we did in the previous example and maybe multiplying by something, in a very special way, but this one is going to be even easier than that because tangent, we know, is sine over cosine. So tangent x over x is all of this times 1 over x. And then maybe now, based on what we did in the example here, you can see a possible way forward. What if we group sine x over x together, okay, into its own function, and then the cosine x downstairs is its own function over here? Well, let's try that out and see what happens. So this limit would then be equal to the product of these two limits by the limit laws, again, providing each limit exists, which we are about to investigate. And certainly this limit, again, goes back to that limit down here, which is equal to 1. And then this limit over here, same old continuity hat on. Question, is this function continuous at x equals 0? Well, let's figure out what the denominator does at 0. Cosine of 0 is 1. Great, so the function is not undefined there. The function is perfectly defined, and cosine of x itself is continuous at 0. So there's nothing going wrong here. This function 1 over x, in fact, is secant x, which is continuous at 0. So I can then substitute in x equals 0, and I get 1 over cosine of 0. 1 over 1 times, oops, excuse me, I just get 1 times 1 divided by cosine of 0, which is 1. So that gives me a bunch of multiplications of 1, with which the answer is 1. Yields the answer of 1. Okay, great. So we evaluated the limit using a slightly different technique, but in the end, similar to what we did that I just erased. You can see the remnants of here. All right, last limit here. This one's going to be an introduction to something else you can do with limits, and there's more information about the technique I'll use in a minute in the book. There's some theorems behind it, but I'll just give you the method, right? So that's the idea for the video. So evaluate this. This is not a typo. This 2 is in fact here, right? If the 2 were not there, then it would be sine x over x. The answer would be 1 based on that result down there. Okay, so how do I do this? First, I'm just going to have you, think about this. Sine of 2x over x. Okay. So if x approaches 0, first of all, I can't substitute x equals 0 because it's in the denominator. This function is not defined at 0, so I can't do the continuity thing. Have to try something different. So here's what we're going to think. Well, x is approaching 0, and this is certainly downstairs, but it's also over here. I'm just multiplying it by 2, but so I'm taking the sine of something that's approaching 0 and then dividing it by something that's approaching 0. Hey, that should remind you of what's going on here, right? I'm taking the sine of something that's approaching 0 and I'm dividing it by something that's approaching 0. So you should have some intuition that perhaps this limit exists and it's equal to some value, and maybe it's related to 1 because, again, this function is so close to the function over here. So that's kind of the first part to think, and how do we kind of get to that endpoint where we relate this limit to that limit? Well, really the only difference here is between this function and sine x over x is the 2 there. So I've written it over here. So what if I divide by 2 and also multiply by 2? You might think, why would I do that? Well, the first thing I would say is that then the limit as x goes to 0 of sine of 2x over x equals 2 times the limit as x goes to 0 of sine of 2x over 2x. Okay? And then we're going to play the same game that we just did a minute ago that I played verbally. So as x goes to 0, 2x goes to 0 because I'm just multiplying by 2. And here's the same 2x. So maybe I can think of this as limit as, I don't know, something like u goes to 0 of sine of u over u, where I'm thinking here of u as 2x. Okay. You might be wondering, how did I know I could do that? And again, my same answer, right? This, number 1, by watching this video, and number 2, just by reasoning as I've reasoned, right? So there's some theory behind this. I'll point you again to the book, which discusses some of that theory. But long story short, right, this limit is equal to 1. Okay, so one thing I did not carry over here, sorry about that, was the 2. This 2 comes along for the ride because it's a multiplicative factor, so this should be a 2 times 1. So the answer actually to this limit is 2. Again, you might not have thought to try this in the beginning, but notice what we did. We just multiplied by 2 over 2, which is just multiplying by 1. And then we pulled the 2 outside, and then what we were left with, we thought about it for a minute and said, hey, the argument of sine 2x is going to 0, and it's the same thing that's downstairs, that's going to 0. That kind of reminds me of what's happening right over here. So then, we thought of 2x as u, and notice that as x goes to 0, u goes to 0. So this limit is the same as that limit. And therefore, we're looking at the same function that we did before, just in a different variable. So then we got 2 times 1, and that gives us 2. So I'll zoom out here and just mention one last little thing here. The point of this video, again, was to talk about trig limits. Notice the different ways that we approach them. And I want you to take away different things from each example. From the first example here, I'd like you to remember that you can multiply by a conjugate, right? So basically the expression in the numerator with a different sign, sign. That may help things. The second thing is you can combine. Notice that, this function, remember we split it into, we took the x to be the denominator of sine x, and we took everything else to be the denominator of the other sign. We did a very similar thing here. Here's tangent. We ended up splitting it this way, right? Keeping the x with the sign again. Why? Because of this fundamental limit down here. That's the second thing that you can take away. And then the third thing to take away from this video is what happened down here, right? We can make substitutions in limits just like we make in other situations and settings in the math that you've learned so far. And provided you can justify that the function that you get is in fact related to a limit then you're free to use that limit. And of course, you can verify your work, you can graph things, you can create tables. There are other ways you can convince yourself that in fact this is the answer you get is reasonable. Okay, that's all for today. Thanks for watching.